translation. Please.
Thanks, Professor, for introducing me, and thanks everyone for attending. So can everyone see my screen right now?
I can.
Okay, thanks. My name is Yangruibo. Today, I will present our work patching as translation, the data and the metaphor. This is a collaboration between Columbia University and University of California, Davis. Let's see what is patching. So patching is a task to fix a buggy code as shown in this example taken from Defect4j benchmark. Here, the variable post is used by mistakes, and an auto-patching tool should replace post with the correct variable PT. Neural machine translation models aim to translate from a source to target language. It typically leverages some form of encoder-decoder architecture where an encoder learns the information from a source language, say French, and the decoder generates sentences to convey the same meaning in the target language, say English. The encoder, a stack of neural network layers, processes the source sentences as a sequence of tokens and encodes it into vector representations. The decoder, also a stack of NN layers, takes such learned representations as input and translates them into another sequence of tokens in the target language. For the NN layers of the encoder and decoder, one of the most popular models in machine translation is the transformer model. It proposes multi-head self-attention interspersed with feed-forward networks that enables both encoder and decoder to attend to any set of tokens across arbitrarily long distances. We adopted this model in our work. In this work, we examine the concept of patching as translation, which regards the program repair as a translation task and applies the sequence-to-sequence model to transform the buggy code to a candidate patch. For example, the translation-based approach will feed this buggy code into an encoder, then the encoder will compactly encode the important information from the input. After encoding the semantics of the buggy code, the decoder of the translation model will produce patch tokens autoregressively. Specifically, the decoder will generate patch sequence left to right, token by token, and every previously generated token is fed back to the model to produce the next token. In recent existing work, we have seen many reasonable results from the application of the patching as translation concept. However, an initial success of transplanted model does not necessarily mean that it is well suited for this new task. Now, it is the time to ask, is it in general feasible to translate buggy code into its repair? So in a high level, we can always evaluate the feasibility of a transplanted deep learning model in three aspects: task, architecture, and objective design. So each deep learning model is targeting on specific tasks, and accordingly, the most efficient architectures and objective functions are selected to serve for these tasks. Other than blindly transplanting a model to a new task, we hope to compare these three aspects that the model was designed for with the intuition behind the new application. So translation is a task that assists people to communicate with each other in different languages. So it preserves the meaning of the source language when translating into a target language. In such settings, the sequence-to-sequence model sufficiently encodes the input semantics, and the encoded information is an excellent guidance for the decoder to produce translated sequence. Architectures for machine translation rely heavily on the autoregressive nature of text. So language is generally produced one word or token at a time in a left to right manner. And in natural languages, grammars are varied across languages. This distinction requires a neural architecture that is able to capture the syntactic transformation between languages. And the attention mechanism of sequence-to-sequence model is effective in learning such variation. As for the objective function of machine translation tasks, the training loss is usually based on the probabilities of the correct tokens. The actual quality of the trained model is measured with BLEU scores or the like that measure the overlap between the generated and ground truth translation. So after understanding the three aspects of the neural machine translation, we also hope to reason about the program repair in the same way. To do that, We collected bug fixing data from more than 8,000 projects and get more than 60,000 bug fixes at the end. We manually checked hundreds of bugs and confirmed most of them are indeed bug fixes. We used this dataset for this paper. Remember, the goal of traditional translation task is to translate the vocabulary while preserving semantics. Now, let's look at the patching example. To fix the bug, the patch actually introduced a new semantics, a new token PT, which is not part of the input vocabulary. So where can the translator learn about this correct candidate? One solution can be expanding the input size to include the buggy context. Here, I include the whole for loop of our example as the buggy context, and surprisingly, the model input contains the correct candidate variable PT. However, can we always see such lucky situation that the correct candidates are very close to the buggy location? To evaluate this, we build vocabularies for both the input and the patch separately. The input vocabulary is built based on the input sequence. It can be either the buggy line itself or the buggy context combined. If the patch vocabulary is a subset of the input vocabulary, we say the patch did not introduce new tokens, and we assume that the input contained enough semantics to repair the program. We see that nearly 90% of the patches introduce new vocabulary related to their buggy source, if no context is given. As the context grows, percentage of unseen words, unseen tokens reduced. However, even if we give the whole file as context, around 50% token is still unseen. The results indicate that to fix the bug, the machine needs lots of contextual information, not only near the buggy location, but maybe across the project or even the project history. Patching as translation heavily relies on similar bugs producing similar repairs, so that the model can learn the transformations that produced patches from those similar training samples and apply the same insight to predict the missing vocabulary at test time. If repairs for similar bugs routinely diverge, as the sample shown, then the model is reasoning about highly ambiguous data and will have to learn a wide range of valid transformations for a single defect. We define such phenomena as the ambiguity of patching, and we argue that if such ambiguity is quite popular in the real-world bug fixing behaviors, the model will suffer to pick up the correct patches. To evaluate whether similar bugs always produce similar repairs, we will calculate the similarity between bugs and patches separately. In the paper, we apply several metrics to evaluate the similarity, but here we just use blue score to explain the idea. In the example, the blue score of the buggy code is 1, called buggy blue, and the blue score of their corresponding patches is 0.12, called the patch blue. Now, we get a data point of 1, 0.12. We plot all these data points across our data set into a heat map to get a conclusive point of view. If bug similarity strongly correlates with patch similarity, we should expect a clear diagonal in the heat map with very few samples in the other region. However, the heat map shows that similar bugs tend to produce patches with typically less similarity, rather than a strongly pronounced diagonal. In the blue region, the bug pairs are highly similar, but the corresponding patches nearly span across all the blue scores from 0 to 1. This demonstrates that for a given bug, the learned program repair history provides a mixed signal of many candidate repairs with distinct semantics. Theoretically, such ambiguity significantly raises the difficulty of learning. To check, in reality, how the model actually performs, we implemented a vanilla transformers model. We evaluated the well-trained model on the test samples, in which 75% of the case will introduce new vocabulary, but the model can only predict 5.6% of the case, which is way lower than the ground truth. To further study the model's capacity in learning the variance and breaking the ambiguity, we also tried allowing the model to beam search across top 25 most probable patches, but it can still only anticipate 14% of the required new vocabulary. Now, we conclude that the patching as translation in its current form is largely infeasible. As we mentioned previously, The nature of autoregressively producing tokens left to right is built into the translation model architecture. And a simple adoption for program repair requires the model to output the entire repair, producing the correct token at each point. However, we can easily see from the example, it might not be the case for program repair. Intuitively, for small bugs like one-line bugs, developers tend to do minor changes to fix the buggy behavior rather than rebuilding all the code logic. Our experiments shows that more than 50% of the samples only added a single token to fix the bug, and 64% of samples have an added distance up to 2. Thus, bug fixing modifications are often limited to just a select few tokens. This confirms our intuition that bugs and patches are highly similar, and patches retain most tokens from the buggy version. This suggests that searching for the correct patch token by token from left to right is a poor use of the search space. A smart program repair tool should just predict which tokens are supposed to be preserved and focus on searching for the ones that require modifications. Also, we have mentioned that sequence-to-sequence model is a good fit to capture the grammar transformation when translating natural languages. We are similarly curious whether this feature is prominent in the conversion of bugs to patches, as such information gives hints about how to adapt machine translation models appropriately. From the example here, we can see that the syntax remains the same, and we also hope to see whether it is the case for most of the bugs. From the experiments on our dataset, we see slightly more than half of our patches preserve the exact syntactic structure of their bugs. Furthermore, the results are starkly different based on whether a patch introduces new tokens. Those that do even more rarely change the syntax, while the other patches are often some kind of permutations of the bug's tokens that very rarely preserves the syntactic ordering. This suggests that the left to right generation process requires the model to both copy an accurate prefix and then generate a single alternative from that context, where the original token was often already close to being correct. Thus, the forced left to right manner is not just inefficient, but misdirected for such bugs. Now, we conclude that the machine translation architecture's generation process is a poor fit for patching. For the objective design, translation model emphasize the per token accuracy for blue-like token overlap metrics to train a model. However, from the example, we again intuitively argue that might not be the case for patching. The bug and repair often share a large identical prefix and suffix with a few different tokens somewhere in the middle. As such, we must question the validity of an object function that values per token prediction quality so strongly. Here, we show the process of training a translation model to predict patches. At the top, token level prediction accuracy increases throughout the first 10 epochs. But after that, it plateaus. It does still increase, but only very slightly after epoch 10. This clearly shows two phases in training this type of model. The model first trivially minimizes its loss through simply copying, but then struggles to predict the correct changes to achieve any more progress. The full sequence prediction reaches just 10% after 50 epochs, which is way lower than the per token accuracy. This can show that it is difficult to transform the per token accuracy to the real patch accuracy. So the training objective is inappropriate for patching settings. The figure also shows that the odds of finding the correct patch in the top 5 generated samples is only a little higher than the top 1 prediction, which suggests that the NMT objective function is weak at sampling a diverse set of plausible candidates, given the natural ambiguity of training samples. Having studied 3 concerns empirically, our results shed light on the effectiveness of a recent competing approach. repairing bugs by synthesizing edits of code conditional on the buggy context. As shown in this example, the model input will be buggy context, and the output of the model will indicate the location to be edited and produce the candidate tokens. Sorry, I have to, yep. Specifically, we propose to make two changes regarding the vanilla sequence-to-sequence model. So first, we implement an edit-based model by emitting two pointers. One is for the insertion starting position, and the other is for the deletion end position. And the decoder will just output the missing tokens rather than the whole patch. Second, we consider context as additional input tokens and expect the model to pay correct attention on the real bug part and the context part. The table shows the results among different models. The edit-based model beats the baseline in both top 1 and top 5 accuracy. Its design is informed by our data analysis, and so it is arguably a better fit for this task. However, although we add a substantial amount of surrounding tokens to the model's input, the resulting model's performance is quite poor, actually performing slightly worse than their context-free counterparts. This is likely due to the challenge of modeling large amounts of context-free information. All this is to say that this model struggles to integrate context, but not the context is redundant. Our empirical analysis helped us review what kind of information to integrate in further improvements, even if we don't know how for now. To conclude, we present a comprehensive study to evaluate the concept of patching as translation, and empirically show that the translation paradigm does not capture bug fixing very well due to the gaps between what program repair needs and what machine translation can supply. We adapt the sequence-to-sequence model used for translation to generate edits rather than raw tokens, which leads to promising improvements. We hope this work inspires more empirical grounded research into transplanting machine learning models to program repair. That's all, thank you. I'm happy to take any questions.
Thank you, Yangruibo. Are there any questions from the attendees? Anyone wants to write a question or to open their mic? No. Okay, so let me ask a question. The way I understand your work, the high level is quite pessimistic, showing that the existing approach is not a good fit in many ways to the problem. But still, I'm not an expert in that, but I thought that there were some successful results in this area previously. So if your empirical results are so negative, how can we explain the early success of these methods?
Yep, that's a quite good question. So basically, we evaluate the concept of patching as translation, and as you mentioned, there are some like existing work that are like performing quite good in the performance. But actually, we also mentioned that this kind of learning-based approach have a hard time to beat all the traditional methods. Probably they are comparable, but this kind of learning-based approach is actually trained based on really large amounts of data compared to the traditional methods. So it is expected to outperform the traditional methods a lot rather than just comparable results. So this is actually the intuition why we argue that this may not be the case to adapt this kind of machine translation model. But I'm not saying that this kind of model will not perform at all, because this kind of models is actually training based on really a large amount of data. And even if it will waste some kind of search space, it can still learn. It can still achieve very good results. Yes. But if we hope to push this field forward for a lot, we probably have to think about this intuition behind this machine translation architecture. Yeah.
I see. Let's see. Okay, so if there are no more questions from the audience, I will thank again the three speakers of this session, and yeah, we'll close this session. Thank you very much for talking and for attending.
Thank you.